Hi, my name is López, and I'm going to talk about this work that I developed with Julian Hammerl and Dr. Hans-Peter Schaub, which is called Dynamic Detection of Nearby Space Objects with Binary Wide Field of View X-ray Sensing. So the main objective of this project is to detect objects in the vicinity of a spacecraft and to do so passively by exploiting space environment interactions that happen naturally. So energetic electrons in the ambient plasma can interact with matter in ways that release characteristic X-ray or Bremsstrahlung X-rays, and we can use those to detect the objects in the vicinity of a spacecraft. And these energetic electrons are present in regions such as geo and cislunar orbits, and these capabilities can be used for detect and track artificial and natural debris, proximity operations, and so on. The inspiration for this using a combination of X-ray sensors comes from the Corson sensor assembly. The difference is that for the cosine law Corson sensors, the relationship between the angle of incidence and the intensity of the signal obtained is known. But with our X-ray sensors, commercial off-the-shelf, the maximum intensity of the signal is not known because it would depend on the distance to the target, on the current plasma conditions, on the exposure time. So we're just assuming that when the target object is within the field of view of one of the sensors, we get a signal, and when it's not within the field of view of the sensor, then we do not get a signal. And so we can use this trigger events, these transitions between no signal and signal and no signal, to obtain information about where the target is located, since we know that the angle between the pointing of the sensor and the heading of the target at those events is the half cone field of view angle of the sensor. So for this work, we are using a 6-sensor configuration with the sensors distributed in elevation and overlapping with each other. The field of view of each of the sensors is 15 degrees, and the platform is rotating. They are mounted on a platform that is rotating with respect to the spacecraft. And here in the middle, you can see an illustration of how of the sensor configuration and how they are rotating with respect to the spacecraft body frame. On the right, we can see a unit sphere surrounding the spacecraft, and the colors represent the visibility, the parts of the sky that are visible from the different numbers of sensors. For coverage studies and average error studies and different configurations of the sensors, I'll refer you to our previous work. So in previous work, we were considering a static target, and in this case, we wanted to extend it to a target that is moving in a simple motion with respect to the observer spacecraft. So one of the first steps was look at a linear time invariant system and look at the observability of the system with the measurement model that we mentioned before, with that geometric relationship between the heading and the target object. So we looked at 3 prototypical cases: a double integrator, CW equations, and a constant angular rate. And with this measurement model, all of these 3 cases were unobservable. So we decided to pre-process these trigger events in a way such that we obtain heading estimations, and these are the measurements that are then going to be sent to a sequential filter. So the trigger events are grouped by proximity in time, and actually the configuration used has proven to be quite useful, because since most of this space covered is covered by overlapping sensors, we get 4 trigger events typically that are very close together, 2 on and 2 off from the 2 different sensors when the target crosses the fields of view. And so we group these trigger events by proximity in time, and we can obtain the headings in a batch least squares method. And with this new measurement model, we demonstrated that the cases that we considered before all become observable. So to kind of do a proof of concept of how to use these measurements, we simulated a constant velocity target trajectory, and we implemented a linear and Kalman filter with a double integrator dynamics and with process noise and measurement noise. And it's worth noting that in this case, the state vector is heading and heading rates, and so that the dynamics do not correspond with the true dynamics seen. But nevertheless, the main objective of this work was to show how these measurements can be used in a sequential filter and not to obtain a super accurate dynamics model. So we just used the double integrator dynamics as a simple case, and we implemented some constraints such as the fact that the heading has to have unit length, and that the heading rate is perpendicular to the heading. And so here on the left, every time it jumps, it's actually because there's a measurement. So we can see the red lines are the 3 sigma bounds, and we can see how this uncertainty grows in between measurements, and that is because of the process noise used. And we can see how the error also increases in between measurements, and that is because the dynamics used to propagate the state are not correct, but we see how the error goes down each time there's a measurement. So that is the expected behavior. And on the right, what we're showing is the error angle, which means the angle between the true heading and the estimated heading. And we see the same kind of behavior with the error increasing in between measurements and then dropping down when there's a new measurement. And with that, thank you very much. And please don't hesitate to email me if you have any questions.